Hello everyone, my name is Paula Argüello. I am a student of computer science in Colombia at the Universidad Industrial de Santander. Today I'm going to present our work titled Optics-less Design for Privacy-Preserving Scene Captioning. To begin with, the image caption task consists of describing scenes in a single sentence captured in an image, as you can see in the following examples. But as you can see, there are images that expose the privacy of the people involved in the scenes. These images may contain infants, elderly patients, or people in environments that should be private. Therefore, our work proposes an approach to the image caption task, but preserving the privacy of the images by using a camera with a refractive lens, and keeping the descriptions of the images at the same quality. Traditional image caption methods use traditional cameras for the acquisition of the input to their method. In addition, most architectures use a feature extractor and a recurrent neural network for the generation of the image captions. Instead, our proposed method proposes by using a camera with a refractive lens to distort the image in such a way that faces or things that should be private cannot be seen clearly. More specifically, we propose an encoder-decoder end-to-end architecture where the training dataset X from the COCO dataset has to enter our camera to generate Y images. Then these images will be fed into a ResNet 101 pre-training in ImageNet to generate the feature map A. And finally, an LSTM with an attention module will generate the captions V. First of all, the encoder consists of a convolution between the X images and a phi point spread function aiding a sensor noise to generate the blurred Y images. This point spread function is produced by the refractive optical element to encode the physical characteristics of an image. This point spread function is defined in terms of the lens surface profile, which is generated and manipulated by the linear combination of Cernic polynomials. Each Cernic polynomial represents a wavefront aberration. Therefore, the linear combination of these aberrations will form the surface profile. The main goal is to learn a linear combination of Cernic polynomials. For the decoder part, we use a state-of-the-art network model in which they use a convolutional neural network for the feature extraction and an LSTM with an attention module to generate the descriptions. We adopt this model but with the input blurred images. In addition, we use a ResNet 101 for the feature extractor. We use a LSTM network with an attention module to generate a caption by computing one word at each time step t, conditioned on a context vector, the previous hiding state ht, and the previously generated word vt. For the loss function, two important aspects were considered to find an appropriate cost function for our approach. The first is maintaining the visual image distortion, and the second is the performance at word generation. Then our loss function is defined as: the first term is a doubly stochastic regularization to encourage the model to pay equal attention to every part of the blurred image. The second term is the multi-class cross-entropy loss to generate a correct sequence of words, and the last term uses the mean square error to maximize the difference between original X and sensor Y images to enforce image degradation. For the results part, we can see on the left the original image of the COCO dataset and on the right the image distorted by our proposed method. Below each of them is the generated caption. Also, you can see the PSNR of the two images in right above. Since there are cameras that can produce the same effect, this Evaluation Studio shows a visual comparison of our proposed method using the optimized lens against from traditional approaches, the focus lens and low-resolution cameras. The figure shows the image and caption outputs of each model. Additionally, we compute and show the PSNR between the original and distorted images by different approaches. As observed, in all approaches, the content of the images cannot be easily recognized, and however, our method achieves the best description of the scene and as expected minimum PSNR. To quantitatively evaluate our proposed approach, we use the standard BLEU and Meteor metrics. BLEU 1, 2, 3, 4 score indicate how similar the candidate text is to the referent text, with values closer to 100 representing more similar text. Meteor metric scores output captions model by aligning them to a set of references. We compare our model against non-privacy methods. These methods use cameras with a standard lens, and the last one represents our proposed model without the optimized lens. Also, we comparison with the privacy methods explained before, the focus and low resolution cameras. Our proposed architecture without privacy obtains the best results because of our training improvements, and the performance of our proposed model does not decrease considerably compared with the non-privacy methods while providing privacy protection. To validate privacy, we evaluate the performance of a face detection network on the distorted images obtained by simulations of our designing lens and compare it with its performance when using normal images. We use the retina face network and perform the next 4 experiments. The first, train the face detection model from scratch by using original images resized. The second, train the face detection model from scratch using blurred images. Third, evaluate the face detector performance, train it on the non-privacy experiment on distorted images acquired using our optimized lens. And last, load the learned weights from the training model in non-privacy experiment and then perform fine-tuning using the blurred images. Fine-tuning an experiment means a way of applying or utilizing transfer learning. As expected, the curves shows that the best performance on face detection is achieved for the non-privacy experiment since the faces are visible on the images. On the other hand, it is observed that the face detector performance decreases when using distorted images acquired by our lens since the model cannot correctly infer where the faces are located. Also, at right, we show the visual face detection results where it can be seen the successful detection of the woman's face when using the model from the non-privacy experiment and the failed detection when using the model from training experiment. In conclusion, this work proposed an image caption model based on attention which promotes privacy of the input images through a refractive optical element, causing a blurred visual effect on them. In this way, the people, objects, and places involved in the input images can be preserved. In addition, we maintain high performance on the BLEU metric with the COCO dataset despite visual distortion. Additionally, we train a face detector on our private images to validate our method's effectiveness. As observed, the face detector failed since our learned distortion preserves privacy. Thank you.